Hi, my name is Arvind. In this talk, Xumiao and I will briefly introduce our work titled A Variegated Look at 5G in the Wild, Performance, Power, and QoE Implications. Commercial 5G has been around for over 2 years, and operators are continuously expanding and upgrading their 5G deployment. Reports suggest that 5G adoption is going to hit 1 billion by next year. This is not surprising given the hype 5G enjoys, as well as the exciting use cases promised by it. However, there exists a vacuum in understanding how 5G as a technology performs out in the wild. For instance, little is known about the power characteristics of 5G. Is it more energy efficient than its predecessor 4G or LTE? Are there any trade-offs? What about 5G's network performance footprint? 5G ecosystem is continuously evolving with different deployment strategies such as non-standalone or NSA 5G, which relies on LTE for control plane operations, and standalone 5G, both of which are here to stay. Coupled with the low, mid, and high band frequency ranges, the 5G ecosystem has become complex to understand. Therefore, we also seek to improve our understanding of 5G's network performance and identify potential issues. Lastly, it's unclear how 5G will impact application quality of experience or QoE, and what could application developers potentially do to leverage 5G technology. To answer these questions, we build a holistic testbed consisting of different 5G smartphone models, external power monitors, etc. Using multiple 5G carriers, we carry out extensive in-field experiments in 2 US cities and conduct a comprehensive measurement study. We have released the dataset and measurement tools. We begin by first talking about the end-to-end network performance. A typical end-to-end path includes the end user or UE connected to the carrier's base station, which is then connected to the carrier's core. The core further acts as the gateway to the internet. Prior work has typically deployed virtual machines in public and private clouds to conduct end-to-end network performance tests. However, due to the known ultra-high bandwidth capacity of 5G, the internet can become a bottleneck affecting our experiments. Our goal was to understand the network performance provided by the carrier's infrastructure in different 5G deployments. But academic researchers like us do not have visibility into the mobile carrier's infrastructure and the policies enforced by them. To overcome these challenges, we take the following approach. Ookla's speed test service is a popular tool for testing network performance. All 5G carriers in our study hosted their servers on Ookla's speed test service. For example, as shown here, Verizon hosts around 48 servers in the US, which are typically located in major metropolitan cities. We leverage the flexibility of server selection provided by Ookla, as well as the carrier's presence to reduce, if not eliminate, the impact of internet-side bottlenecks. First, we look at the latency characteristics of Verizon's millimeter wave 5G. With the UE's location fixed in Minneapolis, we measure latency across all their servers in the US. When tested with the closest server located in Minneapolis itself, we observe lowest latency of just 6 milliseconds. The latency increased by over 2 times when tested with the second closest Verizon server located in South Dakota. Going to either coast increases the latency by a factor of approximately 10 times. We also conduct similar experiments on Verizon's low-band 5G and LTE network. Due to the flexibility in frame structure and control over the transmission time interval in 5G NR, both low-band and millimeter wave 5G exhibits better round-trip times than LTE. Nonetheless, our results clearly quantifies the importance of edge. We conduct similar experiments to measure throughput over millimeter wave. When multiple connections are used, the UE can achieve an impressive downlink throughput of over 3 Gbps across all the servers in the US. However, with a single TCP connection, even after tuning TCP, we find that the downlink throughput degrades as the distance between the user and the server increases. These results again signifies the importance of edge, especially for bandwidth-hungry applications. It also highlights the issues that exist today with current TCP layer mechanisms. The uplink throughput, on the other hand, peaked at around 220 Mbps. Both single and multiple connection tests can achieve peak performance across all the servers in the US. We also conduct network performance and handoff analysis of T-Mobile's low-band 5G services, which are deployed in both standalone and non-standalone modes. We skip them here, but the details can be found in the paper. Next, Xumiao will talk about the power characteristics of 5G.
Hi, I'm Xumiao Zhang. Now, let's take a closer look at the power characteristics of 5G. We first investigated RRC state machine. RRC is a power management protocol. QoE transitions between different RRC states, including connected and idle states, to balance network performance and power consumption. In SA5G, a new inactive state is introduced for more efficient state transition. Using RRC probe and RRC State Inference approach integrated into our management tool 5G tracker, we infer different states and timers for different network settings. Please refer to the paper for the detailed results. We further studied the impact of state transitions on power consumption. When there is no network traffic, the US radio stays active for a period of time before entering the idle state. We find that 5G consumes more power during this tail period than what used to be experienced over 4G. And this number is especially high for millimeter wave 5G. Also, the additional switch from 4G to 5G when the UE promotes to the connected state on the NSA 5G incurs a large amount of power consumption. All this indicates 5G is less efficient in state transitions. Many recent works rely on software API for power readings. To use a hardware power monitor for more precise measurement, we have to remove the smartphone battery and reconnect the battery logic board to the monitor. Besides, the monitor requires an external power supply, so we carry a portable power station together with the laptop. We conducted in-the-wild experiments by walking through a loop with several 5G towers. We also conducted a controlled experiment by hand-holding the smartphone at a fixed location with clear line of sight to a 5G panel. From the control experiment, where we set different target uplinks and downlink throughput during data transfer, we can learn that power increases linearly as the throughput increases, but the power of UE on the millimeter wave 5G increases at a slower rate. Basically, millimeter wave 5G consumes more power than 4G and low-band 5G at low throughput levels, but it becomes more efficient after a certain threshold, around 200 megabits per second. Signal strengths also affect the power consumption, and 5G signal strengths can fluctuate frequently and widely. To better isolate the impact of signal strengths, we divide the throughput from the power to calculate the energy efficiency for different signal strength levels. The energy per bit drops as the signal strength gets better. Looking into the power throughput signal strength relationship, we can conclude that both throughput and signal strength can significantly affect UE power. With the recorded network band information, we also see different bands have varied power characteristics. All the above findings motivate us to seek for a better way for the UE power model, while traditional approaches mostly consider only a single factor. We turn to machine learning-based, data-driven approaches to take into account multiple factors. Specifically, we use decision tree regression. We constructed a power model for different devices, different networks, and different radio technologies and bands. By comparing the mean absolute percentage error averaged across all the network settings, our model, considering both throughput and signal strength information, produces the lowest prediction errors at 5.4%. Now, Arvind will cover the rest.
Thanks, Xumiao. Next, we look at the QoE implications, beginning with video streaming. Adaptive bitrate algorithm is one of the primary tools used to optimize the quality of experience for streaming videos. From the existing literature, we picked 7 diverse state-of-the-art ABR algorithms and put them to test. We focus on 2 metrics here, one, bitrate, and second, video stall time. The desired sweet spot is achieved when the bitrate is higher with lesser stall time. For 4G, we find several existing ABR algorithms work well and fall in the sweet spot. For 5G with millimeter wave coverage, most algorithms do well in achieving bitrate level but suffer with the stall time. On average, we find that streaming over 5G increases the stall time by approximately 58% when compared to 4G. There are 2 main problems causing ABR to suffer over 5G. Number 1, many ABR algorithms rely on throughput predictors to make bitrate decision, but the wild and frequent throughput fluctuations in 5G degrades the prediction accuracy, leading to non-optimal decisions. Secondly, an ABR algorithm makes coarser grained decisions about the chunk quality based on the information it has, with no ability to roll back, say, a non-optimal decision once it's made. In the paper, we propose a simple 5G-aware interface selection scheme for video streaming that can help reduce the stall time without significant loss in quality and at the same time improve energy efficiency. Next, we also consider web browsing application as a case study to understand performance versus energy efficiency trade-offs between 4G and millimeter wave 5G. We find that 5G provides marginally better performance. 4G, on the other hand, uses much lesser power. Therefore, depending upon the radio band and technology, indeed we find a trade-off between performance and energy efficiency. However, challenges lie in deciding which interface to use to load a web page. This might be driven by the desired QoE. More details on this with simple models can be found in the paper. Coming to the key takeaways, we quantitatively reveal the importance of edge over the end-to-end network performance across different radio technologies, 5G carriers, and deployment models. We also highlight key challenges in meeting ultra-high throughput demands. In terms of power, we find that due to the complex ecosystem of 5G, there are several factors impacting power and energy efficiency. We also provide key insights into how upper layer applications should best utilize 5G by balancing the critical trade-off between performance and energy efficiency, as well as become 5G aware. Last but not the least, our study also provides motivation and research opportunity to design intelligent radio or band selection schemes that can meet the desired application QoE efficiently. To conclude, in order to reveal the state-of-the-art landscape of the 5G ecosystem, we conducted a comprehensive measurement study of the commercial 5G services here in the US from and across three key dimensions: network performance, power, and application QoE. Thank you.